So good evening, I'm Calvin Joseph, and today I'll conduct the problem solving and doubt clearing session for the electrical measurements and electronic instruments course, NPTEL course, which was taught by Professor Abhishek Chatterjee of IIT Kharagpur. So I will be giving a summary of what topics were covered in week 3, what are the important points to remember and to note down, and then I will be solving some previous year assignment questions. Okay. So
Good evening, sir.
Good evening. So we will be starting with week 3. So I hope you, okay, my screen is not sharing. So you guys are able to see my screen, right? Okay, so the topics which were taught in week 3 was, one topic was error. Like whenever we do measurements, say we are measuring voltage, current, or wattmeter, etc., there will be some error which will be there in the instrument. Okay, so we want to know like how much is the error, and it is desirable that the error should be 0, but that is not always possible in real life. There will be some tolerance, there will be some error. But what precautions should we take such that the error can be limited? The effect of the error can be brought to 0. Or in case we know that certain phenomenon will happen when we connect our instrument, and how do we compensate for that error such that that error can be brought to close to 0 and we can get an accurate reading. So one is error. Error is there. There is also what is the absolute error also was covered by sir. What is the relative error, etc. All these terms sir had used. So say the current, there is certain resistor, there is certain current flowing. That current is 1 ampere. Okay. Then I will use an ammeter to measure that current. My ammeter will show, it may show 1.01 ampere. So what is my absolute error? My error is the
0.
which the ammeter minus the actual current, that is 1.01 minus 1, that is 0.01 ampere. Okay. Now, if you want to find the relative error, this is known as the absolute error. Okay, so the absolute error divided by either the actual value or the measured value. Okay, so we can take any one. We can take 1 ampere. So it is actually 0.01 ampere divided by 1 ampere. So it is actually 0.01, and it is unitless. It has no unit. Okay. Now, if we have to find the percentage relative error, we just have to multiply it by 100. So it becomes 1. It becomes 1%. Okay, so there's just a 1% error. So suppose why is the relative error important? Like in this case, it is 0.01 ampere is the error. And this error might be negligible when we are measuring 30 ampere, 40 ampere, or very large currents. This error is negligible. But say if you are actually measuring 0.1 ampere and you are getting an error of 0.01 ampere, then it is very large. Then your relative error will increase further. Your relative error will become 0.1, and your relative error will become percentage relative error will become 10%. So that is why whatever error is there, okay, we know that the error is there, but how much is that error with respect to the actual quantity being measured? How much is the deviation? So that we use the term percentage relative error. Okay? And if you want a more accurate and precise measurement, then you'll have to have a more better instrument, more costly instrument, etc. So those are all certain additional criteria. But for you, you must know what is error, what is the absolute error, what is the relative error. Furthermore, is I have something like, say, my quantity is A1 and I'm dividing it by A2. Okay. And my percentage error in this could be like 1%. And the percentage error in quantity A2 is 2%. So whether it is A1 divided by A2 or it is A1 into A2, what happens? This error will propagate. The error will increase, right? So what will be your, suppose this is, say, measured quantity M1, this is measured quantity M2. So the relative error of M1 is going to be, sorry, the relative error of A1 plus the relative error of A2. Okay. Even in this case, it will be relative error of A1 plus the relative error of A2. Okay. So whether you do product or division, your how the error is propagating is similar, because we want to find the most worst case error. What would be in the worst case scenario? How much is the error if I'm doing such a type of computation, such a type of measurement? How is the error being propagated? So we for that these are the worst case possible scenarios of error. Okay. So after error, what did sir teach? Can anyone tell? You guys are going through the videos, right? After error, what did sir teach? Sir also taught measurement of resistance. Okay. How do I measure resistance? One method is I use a voltmeter, I use ammeter, and then I connect a resistance like this. There's an ammeter here, there can be a voltmeter here, etc. And then I will say that this is the voltage V, this is the current I, then the resistance which I must find is V upon I. But this is a crude way to do it, right? Because you know that voltmeter is not ideal, your ammeter is not ideal, and there are certain errors in that. There's certain internal resistances in that, and they affect the actual current or the actual voltage across your resistance. It will differ. Okay. So this is not a good way. So a way to do that is known as the Kelvin's double bridge. Okay, it is similar to my name, but this is different. So there's something known as a Kelvin's double bridge. What you do in this is you have some voltage. Okay. You have a bridge. And in the middle of the bridge, you have a galvanometer. So say this is P, this is Q, this is say S, and this is say R. R is what you want to find. You want to find R. R is what you don't know. P and Q, you can vary it. Okay. Like you can change. You can set that P should be 10 ohm, Q should be 20 ohm, S should be S should be 0.1 ohm. All that you can vary them. Okay. They can be vary. Now this galvanometer will carry a current Ig when this bridge is not balanced. And there is a simple way to know how the bridge is balanced is this P into S should be equal to R into Q. If this condition is satisfied, then we can say that the bridge is balanced. Then we can know that R is given by P into S divided by Q. So you cross multiply. You have to just cross multiply the opposite arms of the bridge. Okay, this is very useful. This is not only for resistance. This can be for a capacitor. This can be for an inductor. It can vary. Okay, like you might soon learn that you can, if you want to measure capacitance, if you want to measure inductance, you can use this bridge technique as well, and it will become impedance. Here in this case, we are considering pure resistances, but when you have inductor capacitor, it will become impedance. and still this formula is valid. Okay, still this formula is valid. So this is a shortcut way if you want to verify if you're confused. This way you can remember. You have to cross multiply the opposite legs of the bridges of that bridge. Okay, this is a Kelvin's double bridge method, and there is also certain sums which we will be looking into. So where we will consider aspects such as what is the resolution of this double bridge, how accurate it is, okay, and what is the sensitivity, etc. We will see. Okay. Till now, do you guys have any queries? Any doubts? So there's Kelvin's double bridge. Kelvin's bridge. There's also something known as Kelvin's double bridge. These are used for measuring very small resistance. Okay. So now we know that to measure that for very small resistances, the four pin terminal resistance is preferred. And you must understand why we have to use a Kelvin's double bridge or something. It is we consider topic of error. Okay, error is problematic only when its relative percentage of that error is very high. Say I have a resistance is 1 ohm, and the error in the measurement of the resistance is say 0.5 ohm. Okay, that's the error in the measurement. So then my percentage relative error will be this 0.5 divided by 1 into 100. So it is 50%. So there's a large error, like around 50% error is there. And this is not acceptable. Suppose my resistance, let us say, was like 100 ohm. Okay. Then in that case, my percentage relative error will be 0.5 divided by 100 into 100. That is like 0.5%. Yes. Okay. So it'll be 0.5%. So this error is insignificant. Okay. It's insignificant. You can neglect it, but this error you cannot neglect it. Okay. So as we are engineers, okay. So as an engineer, or we are becoming engineers, we are studying to become engineers. We cannot say to the point that my resistance is 100.1256 ohm. That is not necessary for us. We want a resistor, say it should be 100 ohm. It can vary, but it should do the job. Okay. But when you want a very small resistance, 1 ohm, what happens is there are some contact resistances. So the resistor, when it is connected to some part, okay, it is connected over here, over here. These small part, which are known as your contact resistance, they introduce error. Okay, these contact resistances are there in the bridge. When you connect the bridge, these contact resistances are there. And now the error which is generated by them is not negligible. It is significant. So to overcome this, there is the Kelvin's double bridge is there, which is used to neglect that error. Similarly, so this is a problem when we do low resistance measurement. Okay. Now, when we have to do high resistance measurement, can anyone tell where will we come across high resistance, or is high resistance required? Hmm? No one knows? Okay. So there are what you know what you say there are insulators. Okay, insulators are important. We we broadly know that materials are divided based on electrical properties into three types of categories: conductors, semiconductors, insulators. So all have their specific requirements, specific application areas. We cannot say that this is not required, this is only required, this is good. Everything has their specific application. So an insulator's job is to not allow current to flow. Okay, that's why the wire which is there, which carries current, it has an insulator on top of it, so that if we touch it, we will not get a shock. And that current which has to flow will only flow through that wire. It will not flow through any other part. So that insulator is like blocking, is like confining the current to flow in the path in which we want. Okay. So that is why an insulator is there. And so it should have very high resistance. So no insulator is perfect. It does not mean that, like, see, you have a wire, okay? On top of it, there will be this insulator will be there, okay? There will be this insulator, etc. And your current will be flowing like this over here. But it does not mean that the current will not flow out. Okay, there can be some capacitive path can be formed, or your that insulator could carry a very low negligible current. Okay, it can carry very low current. So there could be a path which is there, which is through the insulator. Also, we have certain leakage current. That current is known as a leakage current. Okay, so what we would want this leakage current to be, ideally it should be 0 ampere, but it may be in terms of microampere, some maybe 1 microampere, etc. All this, but there will be some certain leakage current. So we want to know how much will that leakage current be. So what we have to do in that case is we have, say, a resistor, maybe some cable is there, right? We apply some voltage, and we also have certain ammeter to check. Okay, so there will be some current which will flow. So now there are various challenges when we want to measure high resistance. We'll require the voltage to be very high, like say around 2000 volt, okay, or 3000 volt, something so high such that some little current will flow. If it is say 2000 volt, then probably you might have 1 milliampere current may flow. See, your ammeter also should be very sensitive. It should be able to measure 1 milliampere. Okay. So there are a lot of challenges when we go for measuring high resistance, right? So, so there's the resolution of the instruments comes as a challenge. To generate this very high voltage is not easy. So what voltage do you get at your home? What is the voltage level or the voltage that you receive to your home in the
230.
socket? Sorry?
230.
Yes, you get at your home, you get 230 volt. From 230 volt, you have to first make it into DC, and then you have to generate to 2000 volt. So all these will require very specialized equipment. Okay. So now you have, like, you're in a big company and they have that equipment, they generate 2000 volt you have given. And now you connect the resistor and then you measure some certain current. But you are checking the current which is only flowing like this. You think that the current is only flowing like this, right? And this is known as the volume current. But there will also be certain current which will flow in the surface. In the surface of the insulator also certain current will flow. This current is negligible when we go for, these resistors which are very like 1 ohm, 100 ohm. Then that current is very low. We can neglect. Okay, that parasitic current is very low. But when we go for resistances which are such high value, your current which is flowing over here, that is your volume current. Let us say that is like say around, or what, let me say, let me take it to be like 0.9 milliampere, right? And the current which is flowing through your surface is say 0.1 milliampere. Okay. So this current used to be neglected. It used to be neglected when the resistances were very small. But this current cannot be neglected anymore when your resistance is very high. Why? Because the current flowing through the resistance is comparable with the current flowing in the surface of the resistance. Okay, so that actually the relative error is more. Okay, the relative error is more. So that is why your concept of error should be spoken in terms of the relative error. Just absolute error, you cannot say that, okay, my this 0.1 ampere difference or 0.1 milliampere difference. That error percentage depends on your specific application area. All right. So when there is certain scenario, say this is like say 1 meter cable. Now assume you make your actual cable is like 1 kilometer. You want to measure what is that resistance. So this volume current, there may be some direct relation, but this surface current will also have certain value. Okay, and which you must consider in your calculations. So that is why there is something known as a guard wire is used. So through the guard wire, you can bypass certain current. Certain current is bypassed through it, and then you cannot use the guard wire and check the actual total current, and then you will get an estimate of how much is the surface current, how much is the volume current. Okay, both these estimates you will get to know. Okay, so there is a good assignment problem is there which we will consider for this. Okay, and the last part which sir taught was the wattmeter. So what is a wattmeter used for? Why do we need a wattmeter?
For measurement of power.
Okay, so measurement of power. And what is the unit of power?
VA.
V is volt ampere, is also this apparent power, but in our case we are considering active power. So it is in terms of watts. Okay, we are considering active power in terms of watts. All right. So power, this active power is the average of your voltage into your current. That average will give you your active power, and that power you want to measure. And to measure that, we use a wattmeter. So wattmeter is basically an electrodynamic instrument. So you guys would have studied that electromagnetic displacement, the torque, is directly proportional to the current through the moving coil and the current through the fixed coil. Okay, the average of them. So torque can be written as the average of the current, and this voltage is also can be written as some voltage by R, etc. So that way, the torque is proportional to the average of I into V. First, this R is a constant. So your torque can be made proportional to your power. In this way, we can make a wattmeter. Okay. In this way, using the concept of electrodynamic instrument, which we studied earlier, which we use the electrodynamic instrument for measuring the current. It used to measure the RMS current. Okay, so we could use it for AC quantities also. Okay? So now, instead of measuring, instead of both the coils, both the fixed coil and the moving coil to carry current, we are making one of the coils to carry current, another coil to carry a current which is proportional to the voltage. Okay, which has the information of the voltage. And using that, we can take the average of the current into voltage, which is the actual power. Okay, so this is the way, this is the logic behind the use of a wattmeter. So wattmeter, it will have a current coil as well as it will also have a pressure coil. So if you see a wattmeter, it will have two terminals. This is for your current C1, C2 or something like this. And this will be your P2, P1, etc. So it will have four terminals. Okay, so these terminals have to be connected, right? So say this is your current coil, this is your pressure coil, and this is your resistor. and this is your voltage source. So this instrument over here, this is your wattmeter. Okay, so it will carry the current and this will have a proportional voltage. Okay, so there are errors which are there. So that's why we have to compensate the wattmeter. All these things are there. So we will study that by, we will look into it by solving some sums. So till now, does anyone have any doubts, any queries?
No, sir.
Okay. So one more thing is, this is a Zoom meeting. Okay, so this meeting will end after some time. So once it ends, then I will again restart the same meeting. So you have to join the same link.
Okay, sir.
So we will consider this question. So if you can see, this is your high for high resistance. Okay, I want to measure high resistance. So what I do is apply a voltage plus minus DC. It is some very high DC voltage, okay, which is difficult to generate. Then that will flow through my resistor and will come out at this terminal, and then I'll measure the current, microampere. Some current will be there. But there will also be certain current which will flow on the surface. Some current will flow internally in the volume of your resistor, but some current will flow on the surface. So there will be a guard ring will be there. So what the guard ring will do is it will collect that current and it will provide a path for that surface current to flow like this. So that surface current will flow like this over here and it will divert over here. If the guard ring was not there, it will continue. But since the guard ring is there, it will divert and come here. So you will measure only the volume current if the guard ring is there. If the guard ring is not there, so this is when the guard ring is there, your current which is seen in the ammeter is only the volume current. But when there is no guard ring, then the current will be the current flowing in the volume of the resistor plus the surface current will be there. Both these currents will come into picture. Oh, my voice is low. Okay. Is my voice better now? Okay. Just hold on. Put the fan on. No. Okay, I actually used the headphones thinking that it would make it better, but I don't know. Probably it is not helping. So what I wanted to say is when the guard ring is there, the surface current which was flowing through the surface of that resistor, the surface current which is flowing through the surface of the resistor gets gets a low resistance path and it gets bypassed. But when the guard ring is not there, the current which will flow through the ammeter will both be the surface current plus the volume current. Both currents will come in my ammeter readings. Okay. So this is the concept which we will use and we will consider. So now the voltage applied is 2 kilovolt. Okay. Achha. So voltage applied is 2 kilovolt. That is 2000 volt. Okay. Your length is 40 centimeter, width is 20 centimeter. Okay. Length is 40 centimeter, width is 20 centimeter, and height is 10 centimeter. So one of the ways which I use for solving sums and which will be very useful for you guys is you always convert all these things into your SI units. Okay. Because it will make your life easier. If you convert, you can again bring it back to centimeter, etc. That you can do later. But first, always you bring it to meter. That is what I do. So 40 centimeter, I write it as 0.4 meter. Width, I write it as 0.2 meter. Height, I write it as 0.1 meter. Okay, so these conversions are important. It takes time to know properly, etc. These might result in some errors if done improperly. So all these things you must not neglect. Huh? So the length I wrote, width I wrote, height I wrote. All these things I've written that this is the value. I brought it converted into meter because I prefer to work in that manner. For me, that is the easier way. Next, they are saying that the current is found to be 6 microampere in the presence of the guard ring and 8 microampere in the absence of guard ring. So when the guard ring is there, the current is 6 microampere. When there is no guard ring, the current is 8 microampere. Okay. So till now, what data is common for these questions, I have noted down. So now the first question is how much is the volume current and how much is the surface current? Okay. So can anyone tell me how much is the volume current?
6 microampere, sir.
How much is the volume current?
6 microampere, sir. Volume current.
6 millions.
6 microampere, sir. Volume
Not willing
current.
to tell. You can tell, you can try. If it's wrong also, there's no issue. This is not your
6
exam.
mic.
Niranjan, Matulagi, Vanchini. How much is the
Sir.
volume current?
6 microampere.
So
6 ampere.
the volume current is actually the current which is flowing in the guard ring. Right? So that is my 6 microampere. Now how much will be my surface current? Yes, correct, 6. So how much will be my surface current? 2. So my surface current will be the current when there's no guard ring minus the current when there's guard ring. That is 8 minus 6. That is equal to 2 microampere. Okay, so till now it was easy, simple. We have found out. Next, they are asking is estimate the volume resistance in mega ohm. Okay, you must note down mega, milli, ohm, what they want. We have to find out that. Okay, estimate the volume resistance and estimate the surface resistance. So now, what is my volume resistance? I need to know. So what is my volume resistance? It is the voltage which is applied divided by the volumetric current which is flowing. And how much is that? Voltage which I applied is 2000 volt. And the current, volumetric current which is flowing is 6 microamperes. So 6 into 10 to the power minus 6. So how much is this? Can anyone tell me? Calculate and tell. You can put in the chat also. Niranjan, Mutualagi, Vanchini. Can you guys tell? You have a calculator with you, I hope.
Sir, 3.33.
Mutulagi, I'm not able to hear you.
3.33.
Okay, it is 0.003. Mutulagi, what you are saying something? Vanchini is saying it is 0.003. What about others? Hmm? Okay, you don't need to be so shy. You can try. So it is 2000 divided by 6 into 10 to the power minus 6. So this actually is 2 into 10 to the power 3. Sorry. This I can write it as 2 into 10 to the power 3. 2 into 10 to the power 3, right? 2, there are 10 zeros, 3 zeros, so 10 to the power 3. Divided by 6 into 10 to the power minus 6, right? So now my volumetric resistance is actually 2 by 6 into 10 to the power. There is this 3. This minus, when it goes to the numerator, it becomes plus. So there's 3 plus 6. So that is equal to 1 by 3 into 10 to the power 9, right? Is 1 by 3 into 10 to the power 9, which I can write it as 1000 by 3 into 10 to the power 6. Now, 1 by 3 is 0.33. So multiplied by 1000, it becomes 333.33 into 10 to the power 6 ohm. But they want a question in mega ohm. So that is actually what 333.33 mega ohm. All right. Now, I actually prefer doing these calculations step by step, so that you guys will know, okay, how exactly you must calculate. Because every time you will not have a calculator. And in the gate calculator also, sometimes it is time consuming to do that. So if you can have these certain steps, if you practice, then you can easily do it. You don't need to always rely on your calculator. Then they ask, what is the surface resistance? So that is actually your voltage divided by your surface current. That is 2000 divided by surface current. We found out to be 2 microamperes. So 2 into 10 to the power minus 6. So how much is this? Can you guys tell me?
1000 mega ohm, sir.
Sorry?
1000 mega ohm.
1000 mega.
1000 mega ohm.
Yes, correct.
Yes.
So it is 1000 mega ohm. All right. So in gate on NPTEL, I think NPTEL also has the gate calculator. So you have to just give the value 1000. Okay. If they are told, I want the resistance to be in terms of giga ohm, then it would be 1 giga ohm, right? Because 1 giga is 1000 mega. So if they are told you it is in giga ohm, then you must give it 1 giga ohm. Hmm? Next, they are saying you must estimate the volume resistivity in mega ohm centimeter. Okay. So now, so what is the volume over here? The volume is what your, like, what is the area in which the current is flowing? The volumetric current is flowing like this. It is the one which is flowing inside that area. It is the one which is flowing inside this cross-sectional area. That and that area, cross-sectional area, is your height into your length. So in this cross-sectional area, your current, volumetric current is actually flowing. Okay. So that is what is height into length. It is height into length. So your volume resistivity is your volume resistance into the cross-sectional area divided by the current path length. So what is your volume? That is your R volume. And what is your area? The area is actually your height into this length. Okay, height into the length L. And how much is the length of the distance or the distance which the current has to flow? It is this W. Okay, so it is L into H divided by your W. So your volumetric resistance you found out to be 333.33 mega ohm. So 10 to the power 6. Your length is 0.4, your height is 0.1, and your width is 0.2. So this is 0.4 into 0.1 divided by 0.2. So what is this value? You guys have a calculator, right? Can you tell me how much is this?
$2,896.
Sorry?
2,896 ohm.
2000 into 10 to the power 6.
No, sir. 2896.30.
Okay. What about others? So the others are not calculating. Mutasagi, Vanchini. Hmm? You should calculate because in exam you have to calculate. So अच्छा, so actually this is not correct actually. So 0.2 into 2 is 0.4, right? So this actually is your 2. Okay, this is 2. So it is 333.33 into 10 to the power 6 into 2 into zero point 0.1, right? So that I can write it as 33.333 into 2 into 10 to the power 6, right? This point, because it is 0 0.1, it point gets shifted. So what is 300 multiplied by 0.1 becomes 30. So 333.333 multiplied by 0.1 becomes 33.333. Okay, then you multiply this becomes 66.666 into 10 to the power 6, right? And this is in terms of ohm meter. Now I can write it as 66.666 mega ohm meter, but they want it in mega ohm centimeter. So what should I do? Huh? So this 66.66
100
mega
से गुना
ohm
कर
meter.
देंगे सर, 100 से गुना कर देंगे,
Sorry?
100 से गुना कर देंगे, 100 से गुना कर देंगे सर।
हाँ, 100 से मल्टीप्लाई करना है. So you have to make it 66.666 into 100 mega ohm centimeter. So it becomes 6666.6 mega ohm centimeter. Okay. So this is the answer. This is the volume. बोलो.
बोल रहे हैं सर यहाँ पे एरिया और लेंथ कैसे दिए सर, थोड़ा सा रिपीट कीजिए।
अच्छा, एरिया और लेंथ में कैसे डिसाइड किया ना? ठीक है, मैं बताता
हाँ
हूँ.
हाँ हाँ
यहाँ पे मेरा लंबा सा रेसिस्टर है. हाँ, मेरा बड़ा रेसिस्टर है. ठीक है. ठीक है, मेरा जो भी वॉल्यूमेट्रिक करंट मतलब क्या, जो करंट रेसिस्टर के अंदर से जाता है, जो करंट ये रेसिस्टर का अंदर से जाता है, तो ये जो करंट अंदर से जाते जाएगा. ठीक है. हाँ, तो करंट जो जाएगा वो कितना एरिया में जाएगा, जितना एरिया बड़ा रहेगा उतना ज्यादा करंट फ्लो हो सकता है. जितना, तो सॉरी, वो कुछ देयर वाज नेटवर्क इशू. ओके. ठीक है, तो मतलब कित, कितना करंट जा रहा है, जो वॉल्यूमेट्रिक करंट है वो ये एरिया में ही फ्लो होगा. जो अंदर का जो एरिया है ना, ये एरिया में ही फ्लो होगा. वॉल्यूमेट्रिक करंट ये बाहर का सरफेस में नहीं जाएगा, सिर्फ ये एरिया में जाएगा. तो एरिया के लिए मेरे को क्या कंसिडर करना पड़ेगा, ये हाइट इंटू ये जो डिस्टेंस है जो एल है, एच इंटू एल. ठीक है. और कितना डिस्टेंस के लिए वो जाएगा, ये जो करंट है वो अंदर से ऐसा अंदर से जाता जाएगा, इतना तक, इतना डिस्टेंस जाएगा. तो वो जो इतना डिस्टेंस जाएगा वो क्या है, वो विड्थ है, वो ये डब्ल्यू है. ठीक है. इस सेटअप जो स्क्वायर, जो रेक्टेंगुलर, जो क्यूबॉइड शेप है, इसमें मेरा एरिया क्या हुआ, ये जो हाई, ये डिस्टेंस है और ये डिस्टेंस, और जितना लेंथ वो ट्रैवल करेगा वो ये डिस्टेंस हुआ. करंट कितना लेंथ जाएगा, इतना लेंथ जाएगा. तो इसलिए मेरा रेसिस्टिविटी क्या हुआ, ये एरिया डिवाइड बाय करंट पाथ लेंथ, वो हुआ वॉल्यूमेट्रिक रेजिस्टेंस इनटू लेंथ इनटू जो एल इनटू एच बाय डब्ल्यू. ठीक है. ठीक है. और कुछ डाउट है?
नो सर।
Okay. So this is for the volumetric resistivity. Now we will go for the surface resistivity. तो ये जो सरफेस रेसिस्टिविटी है वो सरफेस रेजिस्टेंस इनटू पेरिफेरल लेंथ, जो डिस्टेंस में that surface current will flow, okay, divided by the length of the path. So I will explain. If you see this, I'll take one more of this. So we want to find the surface resistivity, okay? So now, what is the so when we are considering the surface current, that time guard ring will not be there. So your surface current will be the current which will flow on this surface, okay, on the surface. On this surface, on the top, it will flow. It will flow on this side also, and from the bottom also it will flow. So the current will flow in this part, in this part surface, this part. And then it will flow like this, it will flow like this, it will flow like this. Okay, it will flow like this, right? And in this cross-sectional area, that is this, in this area, not area, actually this cross-sectional length. Okay, the current will flow in this, for this H area as well as this L area. So the peripheral length, now for a rectangle, your area is, in this case, it is H into L for this rectangle. Okay. But your cross section length, what is the length of the periphery, or you can say the periphery of your rectangle, that is given by this height, this H plus this L into 2. One H at this side, one H at this side, one L at this side, another L at this side. So 2 times of H plus L. Understood?
Yes.
So this is my cross-sectional length I found out. Now, how much is the distance that this current will flow? It will flow from here to here. So that distance or the length which it will flow is given your W. So your surface resistivity is given by R surface into 2 times of H plus L divided by your W. Okay. So your surface resistivity was 1000 mega ohm into 2. Your H was 0.4, your L was 0.1, your W is 0.2. So can you calculate and tell me how much is this?
Five thousand around.
How much?
5,000 around.
5,000, huh? Okay. It'll be 500 if I'm not wrong.
Yeah, sir.
Oh,
5,000. 5,000, sir.
Yes, correct. 5,000. So this will be 5,000. And what is the unit? It will be 5,000 mega ohm. 5,000 mega ohm. Because this is in length divided by length gets cancelled. So it retains this unit of this, R surface. Okay, it's in mega ohm. So till now, do you have any queries? Okay, so if you have query, you can stop me. So now,
सर यहाँ पे जैसे गार्ड वायर को नेग्लेक्ट किया,
क्या हुआ?
गार्ड 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 रिंग जो है सर उसको क्या नेग्लेक्ट किया है?
हाँ, अगर गार्ड रिंग नहीं रहेगा,
गार्ड रिंग,
तो क्या होगा, वो सरफेस करंट भी मेजरमेंट में आ जाएगा। हाँ, पर ये गार्ड रिंग तो सिर्फ मेजरमेंट के लिए है, मतलब ये सरफेस करंट फ्लो होगा। जब ये गार्ड रिंग होगा, क्या होगा, वो सरफेस करंट बाईपास हो जाते हैं। ठीक है।
ओके सर।
हाँ, now what will happen is your length. What they told is this L is being made 160 centimeter. So now your L new has become 160 centimeter. That is, it become 1.6 meter. Your L old was how much? L old was L old was 0.40 centimeter, 0.4 meter. Your L old was 0.4 meter. Now your L has changed. Now this your resistivity will remain constant, but your resistance changes. Your resistivity will remain constant. That is the resistivity per that length, per that area. Based on that, that will remain constant. But the resistance will depend on how much length. If you increase the length, the resistance will increase. If you make the length less, the resistance will decrease. But your resistivity will be the same. If your length is 1 meter, if your length is 100 meter, your resistivity will remain the same. That is why your resistivity is important to calculate. So if you calculate your resistance, you will have the base. Then whether you increase or decrease, accordingly, your resistance will change. But your resistivity remains constant. So now, your volume resistance, nu. Your volume resistance nu is what? Your volume resistivity into the length of your current path divided by the cross-sectional area. So the volume resistivity we had calculated was 66.66 in mega ohm meter. I prefer always to use this SI unit, meter, all that. I don't like centimeter. Okay, so I'll use that. So that is 66.66 mega ohm. So that becomes 10 raised to power 6 ohm meter. What is the length of the current path? So if you see, W is your current path length, and that is not changed. What has changed only is your L. Only this has changed. So that will become into your W, into your H, into your L, mu. Okay. So this is equal to 66.66 into 10 to power 6. Your W, I think, is 0.2. Your H is 0.1. Your L has become 1.6. Okay. So how much is this? So if you calculate it, it comes out to be 83.325 mega ohm. And your volumetric current will be equal to your voltage remains the same. Mu, our volume mu, So that is 2000 divided by 83.325 into 10 to the power 6. So what is this? It comes out to be 24 into 10 to the power minus 6 ampere. That is your 24 microampere. Okay. Any doubts in this?
No, sir.
Okay. Now what about my surface resistance? That is my surface resistivity into the length of the current path divided by the periphery length. Okay. So my surface resistivity we found to be 1000 mega ohm. No, it was 5000 mega ohm. 5000 mega ohm. So 5000 into 10 to the power 6. The length of current path is W into 2 into L plus H. L has changed. So it is 5000 to 10 to the power 6 into W is W I think is 0.2. 0.2 into 1.6 plus 0.1. So what is this value? What is this value? Yeah. This 294.11 mega ohm. So that is 294.11 mega ohm. So my surface current actually will be voltage by R surface, that is 2000 divided by this 294.11 into 10 to the power 6. So can you calculate how much is that?
$6.8.
Yes, 6.8. So it becomes 6.8 into 10 to the power minus 6. So it is 6.8 microampere. So the current which will flow when there is a guard ring is just my volumetric current. That is 24 microampere. But the current which will flow when there is no guard ring is the volumetric current plus the surface current. That is 6.8 plus 24. That becomes 30.8 microampere. Okay. So I hope this question is clear for you guys. Any doubts? Any doubts or queries? So all these links I will be uploading. So this video, once the meeting is done, then I will merge, edit and everything, and I'll upload it on YouTube. Okay. And then also the lecture notes I will upload on a drive. So the link I'm pasting here. So the drive link is where these notes will be converted in PDF and uploaded. So you can go through these. So you will have these step-by-step things will be available for you. So you can refer to it. Okay. And then I've also put the YouTube channel link where I will upload these videos. So you can access the videos from there. Okay. So I'll try as fast as possible to upload the video because it takes some time. And the drive link will have the notes. So this drive link has the notes of week 1, week 2 also, which I have conducted. And the YouTube channel also has the week 1, week 2 video also. So you can refer to it if you have any doubts and queries. Okay. Your doubts also, you can post it in the chat in YouTube if you have any other queries. Okay. Or else in the next session also you can join. So these sessions are held every week at on Wednesday, on Monday between 6 to 8 p.m. So now we have solved these sums. Now we will go for this bridge network. So this bridge network is there, right? So P is given to be 100 ohm, Q is given to be 100 ohm, and E is some particular voltage R. So this R is varied. So at the condition when X is equal to P into R by Q. At this condition, when this is satisfied, then the current to the galvanometer will be 0. And that is what we decide. Then we say that the bridge is balanced. So what they do typically is P is fixed, Q is fixed. R is changed, R is varying. And at some particular R, the current to the galvanometer is 0. Then we apply this formula and we will find what actually is the resistance X, which is unknown, which we want to find. All right. So now they have given that P and Q is fixed is 100 ohm. And they say that when R is 100 ohm, we are finding balance. When R is 100 ohm, a balance is found. So they are saying R also is 100 ohm. If R is 100 ohm, then 100 into 100 divided by 100 is how much?
100. 100.
What is X?
100, sir.
Yeah, so it is 100 ohm. Okay, so my X is found out to be 100 ohm. Now they are saying the resistors P, Q, and R are 1%, 1%, and 2%. They have inaccuracy. So we want to find the inaccuracy of measuring X. Okay. And we must ignore all other issues or uncertainties. So this, it has 1% for P. Q 1%, R 2%. So delta P 1%, delta Q by Q, the relative error is 1%. delta R upon R relative error is 2%. So they are saying, what is my relative error? Delta X upon X. That is the question. So it is a function which has both product and division. So that relative error is given simply by this form. Delta P upon P plus delta Q upon Q plus delta R upon R. That is 1 plus 1 plus 2. That is equal to 4%. So I don't need to do any calculations. I don't need to put the values. I just know this formula. Because it is product and division, it is plus plus plus. It is 1 plus 1 plus 1, 2%. So it is effectively 4%. My inaccuracy in X, the measurement inaccuracy is 4%. Okay. So now, any doubts still here?
कैसे हुआ सर ये?
Sorry?
कैसे हुआ सर ये?
If there was?
ये वैल्यू कैसे?
अच्छा, सुनाई नहीं दे रहा. You can put in a chat if you want. Okay. So now they're saying we have to find the resolution of measuring X. We have to find the resolution. Okay. So what do you mean by resolution? Means how are the small values which you can measure using this bridge? So P is fixed as 100 ohm. Q is also fixed at 100 ohm. And your X is given by P by Q into R. P and P cut gaya. So X is actually just equal to how much is R. Now R can be changed. Suppose R was 100 ohm, right? It can be changed only in steps of 0.1 ohm. So R can either be 100 or it can be 100.1 ohm. It could either be 100.2 ohm. It could be 100.3 ohm, but it cannot be 100.25 ohm. This is not possible. These are possible. So the steps in which R can change is only 0.1 ohm. So that is how small I can change R, right? And if I can change R only in these small steps, then my X also, which I can be measured in only these small steps. Okay. So my resolution in measuring X is 0.1 ohm. Okay. Is there doubt in this? Okay. So now they're saying suppose there's a 0.1 increase in X. Then what voltage E is required such that they will produce a 10 microampere unbalanced current through the galvanometer. Okay. They're saying we want Ig to be 10 microampere. And X has changed by X plus delta X. It has become 100.1 ohm. Okay. Now, how much should this E be such that the current Ig will be 10 microampere? So, this E, we have to find out this E. P is given, Q is given, R is given, X also is given. They told X is actually 100 plus 0.1, that is 100.1 ohm. Okay. So, and they're saying this current should be 10 microampere, the current through the galvanometer. Okay. Now, what do? We do the Thevenin's voltage, we do. We remove this from the circuit. We will find the Thevenin voltage. We have to find the Thevenin resistance. And then we can find the current, Thevenin current, we can find it through this method. So now we have to find the Thevenin voltage. There's across this A and B. So what I will do is, so the current will flow like this, or it will flow like this and flow like this. So the voltage at A is this E into this x plus delta x upon P plus x plus delta x by resistive divider rule. So that is VA is E into 100.1 divided by 200.1. That is 100 plus 100 plus 0.1, 200.1. Okay. Your VB is equal to E into R divided by R plus Q. That is E into 100 divided by 200. That is E by 2. Okay. So now my V Thevenin is VA minus VB. That is E into 100.1 divided by 200.1 minus half. So how much is that? So that becomes E into 2.49875 into 10 to the power minus 4. All right.
Right, sir.
That's my V Thevenin. Now I have to find my R Thevenin. What is my Thevenin resistance? So if I see over here between A and B, P and Q are in series. X and R are in series. And then they are effectively connected in parallel. So that will be P plus Q is parallel to X plus delta X plus R. That is 100 plus 100 is parallel to 100 plus 0.1 plus 100. So how much is this value? So this becomes 100.0249 ohm. So now what we can do is, I know my V Thevenin. I know my R Thevenin. I know my galvanometer has resistance, which they have told is to be 800 ohm. Okay. RG is 800 ohm. And this current to the galvanometer, which is my Thevenin current, should be 10 microampere. Right? So it will be, my I is actually VTH by RTH plus RG. That is E to 2.49875 into 10 to the power minus 4 divided by 100.0249 plus 800. And this I should be equal to 10 microampere. So if you calculate, your E is 10 into 10 to the power minus 6 into 900.0249 divided by 2.49875 into 10 to the power minus 4. So if you calculate this, how much you are getting? So if you calculate this, you'll get E is to be 36.019 volts. Okay. It comes out to be 36.019 volts. So any doubts in this?
No, sir.
Okay. Now, now we will consider some questions regarding to a wattmeter. Okay. Suppose we have this voltage of 120 volt and there's a RL is 80 ohm. There's a wattmeter which we are used and it has a current coil of 14 ohm, pressure coil of 700 ohm. So now we have to use the wattmeter. What we will do is, what is the power delivered by this source to the load? So this is 120 volt. This is your load of 80 ohm, right? There's a current which is flowing. How much is that current? 120 by 80. Can anyone tell me how much is it? So many of you are there. Vidya is there. Family is there. Manchini is there. Niranjan is there. Tell me.
1.5, sir. 1.5.
It is
1.5, sir.
Yes, correct. It is 1.5 ampere. Okay.
1.5.
Correct. So the power which is delivered by the source is the voltage into the current. That is 120 into 1.5. And how much is that? That is actually 180 watt.
180, sir.
Okay. How much is the power consumed by this load? Power consumed by the RN load is 1.5 square RL, 1.5 square into RL. That also will come out to be 180 watt. So the power generated by the source is consumed entirely by the load. Okay. So that is a simple one, very simple, nothing is there. We have found out. So ideally in this circuit, if you connect a 120 volt battery and you connect it across 80 ohm resistor, the power which is dissipated should be 180 watt. But now we want to use a wattmeter to measure. This is what should happen theoretically, but how do we measure in real life? We have to use a wattmeter. So we will connect a wattmeter. But the wattmeter's current coil has a resistance of, it has a resistance of 14 ohm. 14 ohm. And the resistance of the pressure coil is 700 ohm. Okay. These are the non-angularities. These are the parasitics which are in the circuit. So now there are many sums, but we will consider certain examples. So suppose it is connected in this fashion. Suppose it is connected like this. Okay. Now, how will it? Now, this is where the current is flowing. So, this is the current and this is the voltage which is applied. There's a current coil and there's a pressure coil, and these together form your wattmeter. So, your wattmeter shows the average power. So, now, effectively, how this circuit looks like. Let me draw it by the side of it. Your E, your RPC, your RCC, and your load RL. Okay. So this is the current going through your current coil. This is the current which is going through your pressure coil, and this is a load RL. So now, how much is this current? How much are these voltages? We'll find out. So your current through your current coil is given by your E divided by your RCC plus RL. Okay. So that your current through your current coil, your E is 120, your RCC is 14, and your RL is 80. So this 120 by 94. Can anyone calculate how much is that?
One 1.27.
1.27, sir.
So it is 1.2765 ampere.
27. 2769.
Yes, correct. The current through your pressure coil, that is a current going over here, is your voltage E divided by the resistance of your pressure coil. Right? So how much is that? It is 120 divided by 700. How much is that?
So 0.171.
Correct. It is 0.1714 ampere.
1714.
Correct. So now what is the total current coming out of this? The total current coming out I, if you apply KCL, this I flowing to the current coil plus I flowing to the pressure coil. So the current is I is given by I current coil plus I pressure coil. So how much is this?
1 point.
So it comes out to be 1.448 ampere. Okay. So now, how much is the power which my source is giving? The power which my source is giving is E into I. Right? So the power which my source is giving is E into I. How much is that? 120 into 1.448. So how much is that?
One 173.76.
Yes. So it is 173.76.
173.
Correct. It is 173.76 watt. But if you remember earlier, when the wattmeter was not connected, how much power it was giving? It was given 180 watt. But now once you have connected the wattmeter, what has happened is there's a pressure coil, there's a current coil, more resistance is added, etc. Right? So the current which is drawn is less and the power which is delivered is lower. Okay. So now, how much is the power delivered to the load? How much is the power delivered to the load? It is a resistor, it will consume power. So that is the current to the resistor, the square of the current into the load resistance. Right. So power delivered to my load is actually ICC square into RL. ICC is 1.25765 square into RL is 80 ohm. So how much is it?
130.356.
Yes, it is 130.35. Now, what is the power measured by a wattmeter? What is your power which your wattmeter is measuring? Your wattmeter you have kept so that it can measure the power, but what is it measuring? It will measure the current through the current coil into your voltage in your pressure coil, right? What is the current through your current coil? Is this 1.2765, correct? What is your voltage across your pressure coil? So the voltage across the pressure coil is this directly this E, that is 120 volt. It is directly because it is directly connected. So that is equal to 1.2765 into 120. So how much is this?
One 53.18.
Yes, so it is 153.18 volt.
0.18.
Yeah. So you see there's so much of error. The delivered power is 130.35 watt. But how much is my wattmeter is measuring is 153.18 watt. And there's so many losses are there. In ideality, when the wattmeter was not there, it was 180 watt was the power which the source was giving. 180 watt is the power which was delivered to the load. And you wanted it to be like that. You wanted your load and you wanted to measure that 180 watt. And so you added a wattmeter. But once you added a wattmeter, because of the practical construction, because of the parasitic resistances, non-ideal resistances, your power delivered to the load is changing, and the power which the wattmeter is measuring is still not equal to the power which is being delivered to your load. It is still changed. Okay. So this is a practical condition which has happened. Any doubts in this? Okay. So now what we do is, this is figure 1. In figure 2, it comes out in this format. Okay. Instead, the pressure coil be connected directly across my resistor. So the circuit becomes resist current coil, pressure coil, RL. Okay. Now, how much will be the current and voltage? So this is the current to the current coil. This is the current to the pressure coil. This is the load current. So the effective resistance seen by the voltage source is your RCC plus RPC parallel to RL. RCC is 14. RPC which you have is actually 700. Parallel to RL is your 80. So that comes out to be how much? 700 into 80 divided by 780 plus 14. It comes out to be 85.794 ohm. Okay, it is 85.794 ohm. So your current ICC is your E upon R effective. That is 120 divided by 85.794. What is this 120 divided by 85.794?
1.3986.
Yes, it is 1.3986 ampere.
86.
Okay. Now, what will be my current through my pressure coil? The current through my pressure coil by current division rule, it is ICC into RL divided by RPC plus RL. So that is actually 1.3986. RL is actually 80 divided by 80, which is RL plus RPC is 700. So how much is this?
0.15.
Yes, it is 0.1434. The current to my load is ICC minus IPC. That I will get it to be 1.3986 minus 0.1434. How much is that?
1.25.
So this 1.2552 ampere. So now again we can find what is the
1.25.
yes, correct. So the power delivered to your load is equal to IL square into RL. So how much is IL square? So it is 1.2552 square into your RL is 80. So how much is this?
126.04.
Yes, it is 126.04 watt. But what is your wattmeter measuring? Your wattmeter is measuring the current to the current coil into a voltage in your pressure coil. And what is the voltage in your pressure coil? It is the current to the pressure coil into the resistance of the pressure coil, right? So that is equal to 1.3986 into the current to the pressure coil is 0.1434 into the resistance in the pressure coil, that is 700. So how much is this?
140.39.
Yes, so it is actually 140.39 watt. Okay.
Yes, sir. 140.39.
Yes, correct. Exactly. So there is an error, still there is an error. Power delivered is 126 watt, but the wattmeter is 140.39 watt. So there's an error, right? There's an error. So now there is something known as a compensated wattmeter. We will be using what is known as a compensated wattmeter. So what happens is current is flowing the current coil, but they also have a compensating coil, and the effective flux which is generated is dependent on the orientation of the current coil and the compensating coil. So using that, they sort of cancel out that current which is causing the error. Okay. So we will see a sum. Let us see this. So this is my compensated wattmeter. Okay. So now, how is my circuit? This is the current to the current coil. This is the current to the pressure coil. This is the current to the load. There is the current going to the compensating coil. And that current is actually the current to the pressure coil. Okay. Now, if you see at this dot, the current is entering into the current, CC current is entering into the dot. But at this dot, the current is leaving the dot. So those magnetic fields will oppose each other. They are not adding, they're opposing each other. Okay.
Yes.
So this is basically the internal construction of the wattmeter. These coils are wound in such a manner. Right? So now what we do is we will draw the equivalent circuit of this. So if you draw, it will be, sorry, this is your E 120 volt, the resistance of your current coil. They have told that you consider the compensating coil and the pressure coil as one equivalent resistance. That is my RPC, and this is my load. This is my RL. Okay, this is my RL. Now, this is my current to the current coil. This is my current going to the load. This is the current in the pressure coil. So if you see this circuit, it is same as this circuit. Exactly same. Only there is a certain compensating coil is there. So now what we will do is we know already what is IC, IL. We know what is my IL. We found IL to be 1.2552 ampere. We found the ICC is equal to 1.3986 ampere. And we found the current to the pressure coil is equal to 0.1434 ampere. Okay. Now we want to find the power which is read by the wattmeter. What is my wattmeter reading? So the wattmeter will read the current in the current coil minus the current in the compensating coil into the voltage across my pressure coil. Right? So that will be equal. So my ICC minus I count, and my I count is my current to the pressure coil. That is equal to my ICC minus my current to the pressure coil into my VPC. Okay. So that, if you see over here, if you apply KCL over here, you will see that ICC minus IPC is actually equal to IL. So it will be your IL into your VPC. And if you see over here, this actually is your VPC. The current across your RL is actually this VPC. So it actually is equal to your IL into your current across your RL, which is equal to your IL into RL. So it is equal to your IL square into RL. So using this method, using this compensated wattmeter method, what we are able to effectively achieve is that we are able to measure the actual power which is being delivered to the load. So if you compute this IL square into RL, that is 1.2552 square into 80. How much is this? Let us calculate. That becomes equal to 126.04 watt. Okay, it is 126.04 watt, which is the actual power which is being delivered to your load. So earlier, because there was no compensating coil, there was this error. What your wattmeter was measuring earlier was ICC into VPC. right? So what was happening is it should actually measure what? It should actually measure IL into VPC. But instead it was measuring this ICC into VPC. So what we did was we connected a compensating coil mechanically into the wattmeter such that your ICC current will be compensated with the extra current which is flowing through your pressure coil, such that the effective field which is generated by your coil will be equal to your current which is flowing in your load resistor. Okay, so this is the function. This is a rule. So how you must know what is happening is you must see the polarity of your dots. The current which is entering in and the current which is leaving out. Okay, when it happens, then they are subtracting. When both are entering in, then it is additive. Okay, so any queries in this? No questions? So all these things, these notes I will upload on the drive. If you want, I'll again put the link. So these notes I will upload on the drive. This recording also I will upload on the drive on YouTube channel. Okay. So you can access it over there. So if you have any doubts, any queries, you can ask it either on the YouTube video or you can ask it in the next session also you can ask. So basically what we did today in the solving sums was we considered what would happen in a high resistance measurement, what would happen. First we did the complete overview of what was taught in this week. So a quick brush up for you. Okay, so if you have gone through the videos, you can easily remember what was taught. Then this high resistance measurement, how there's surface current, how there's volume current. Then we found out how the resistances, we found out the resistivity. The main point to remember is this is a very important point, is your resistivity is constant, but your resistance changes depending on the length and width, all that. Okay. Then we changed, the length was increased. Then how the resistance changed, then how the current changed, then the surface current also changed, then the readings also will change accordingly. Then we consider a case when there is a double bridge, when there's a Kelvin, when there's a bridge network. Okay, this is not a Kelvin's double bridge, this is a simple bridge. And then we found out what should be how to find the resistance, how to find the accuracy, inaccuracy we found, what is the resolution also we found. Then how in case some sudden change happens, how it should be sensitive enough. This 10 microampere is what? This 10 microampere which we want is like what small current will cause the deflection in the galvanometer to be visible. Okay, only if the deflection current is more than 10 microampere, then only you can see a deflection in the current. So this is basically we are trying to find what is the sensitivity of your resistance measurement. That sensitivity is also dependent on the galvanometer resistance and how sensitive the galvanometer is. So that is why we use this Thevenin equivalent to find out. Then we consider what is a wattmeter, how do we connect it, how it is changing. When it is connected in the circuit, the current is changed because of the resistance in the pressure coil, the resistance in the current coil. Then how that the power which is measured is not equal to the power which is delivered. So the wattmeter will measure more power than the power which is delivered. It measures more. In this case also, as well as in this case also. Okay, if you want, you can also find a relative error also you can find. I've not done that because of lack of time, but you can do it and you can tell whether this is better or this is better. that depends on the RCC and RPC. Then if we can use if we use a compensated wattmeter, how it is compensating for all this. Also, we consider how it is removing that error, the error which we don't want. We don't want ICC, we want to measure IL. So how by flux cancellation, it is able to generate a current which is proportional to IL, and it is able to measure the actual power delivered to your resistor. Okay, so this is what we did in this session. This will be uploaded on YouTube, as well as these notes will be uploaded on the drive. Okay, so any doubts? Okay, so if there's no doubts, I'll end this meeting and we'll end this session. Okay, so thank you for joining and all the best
Thank you, sir.
in learning this.
Thank you, sir.
Yeah, thank you.